We're considering first-order systems of linear homogeneous DEs. These systems have the following form. Now, this matrix P is a matrix function. Generally, we want these matrices to be square. Now, in the previous lesson, we discussed that every system of this form has to have a fundamental set of solutions. So this is essentially a basis for the solution space. Now, if it's an n by n system, it has to have exactly n solution vectors. The general solution is formed from this fundamental set by a linear combination. Now, if you want to determine whether or not something is a fundamental set, you check its Wronskian. So you put all of those solutions into a matrix called the fundamental matrix, and you check its determinant. If it really is a fundamental set, these vectors must be linearly independent, and that means the determinant will be non-zero. All of that is great, but how do we actually find these solutions, x1 through to xn? Remember that when we have a first-order scalar equation, and if it's homogeneous like this, we know that we can try solutions that are e to the lambda t. If we take the derivative, we'll get a lambda e to the lambda t. We plug this in. What we'll end up finding is that for certain lambda values, we'll get a solution. So this tells us what the lambdas have to be. So our solution will be e to the minus at. Well, let's try the same thing here. For the special case, and it's special but common, so for the special case of this p of t being a constant matrix, our system is x prime equals ax of t. We are going to let x of t be e to the lambda t, but it has to be a vector. So we are going to multiply it by some non-zero, and that's very important, constant vector. We want it to be non-zero because we know that this system always has the trivial solution, but we want to see if it has non-trivial solutions. If we were to do this, we need to take the derivative of this expression. And again, according to the chain rule, this is simply going to be lambda e to the lambda t times that same constant vector. Remember, by linearity, when you differentiate a function times a constant, all the constants get to go out. So if we were to sub this into the DE, we'll get lambda e to the lambda t times v is a times e to the lambda t v. Now, this is a constant. By linearity of matrix vector product, this can go outside. So we'll have lambda e to the lambda t v is equal to e to the lambda a b. We can reorganize this, and we'll get av minus lambda v equals 0. We know this term will never be 0. One other thing that we can do is rewrite this as a minus lambda times the identity. Remember, all the dimensions have to match, and 0. We've got a bit of an aha moment. To find non-trivial solutions, we need to solve an eigenvalue problem. This matrix here is exactly the matrix that we get when we talk about eigenvalue problems. So if you recall, in an eigenvalue problem, we need to find a lambda. And in second, we need to find this v. So how do we do this, right? If we are interested in non-trivial solutions, this matrix here, a minus lambda I, this matrix cannot be invertible. And if this matrix cannot be invertible, we need to find lambda such that the determinant of this matrix is exactly 0. Remember that the determinant determines whether a matrix can be inverted. We want it to not be invertible. So we want the determinant to be equal to 0. Solving this equation is going to give us the lambdas that do that. And then we are going to find the v's using these lambdas from above, and we are going to look for non-trivial solutions. So if I have a system where this is the matrix, negative 2, 3, 1, negative 4, I would like to solve x prime equals ax. We are going to let our solution form be e to the lambda t into v. And when we do that, we take the derivative, we'll get lambda e to the lambda t into v. If we sub it in, this is going to lead us right back to a minus lambda iv equals 0. Because we want to find non-trivial solutions, we need this matrix to be non-invertible. So we need, number one, the determinant of a minus lambda I to be 0. So we need to form a minus lambda I. So the matrix a minus lambda I is going to look like this. It'll be negative 2 minus lambda, 3, 1, negative 4 minus lambda. So if we take the determinant of that matrix, it's going to produce a polynomial equation. We'll get a negative 2 plus lambda, and if we factor out the negative on the other one, both of those signs will change to a positive. Subtract 3 is 0. So this is the equation we want to solve. This is called the characteristic equation. We'll get 8 plus 6 lambda plus lambda squared minus 3 is 0. Lambda squared plus 6 lambda plus 5 is 0. And it's a second degree equation. If we factor this here, we'll get a lambda plus 5. Lambda plus 1 is 0. So lambda will be negative 1 and negative 5. So the second step in this process is to find the eigenvectors. So we have to find V by finding the non-trivial solutions to this problem for each lambda that we've just constructed. So if lambda is negative 1, that means we now have to solve A plus I, V equals 0. So if we take the matrix that we had from above, we'll have a negative 1, 3, get a 1, and a negative 3. We'll get 1, negative 3, 0, 0, 0, 0. And this is going to tell us that C1 is 3, C2. When we form this vector, C2 will be a free variable. We can take it out and we'll be left with a 3, 1. So in fact, we are going to call this V1, the first constant vector, and we'll take our solution x1 of t to be e to the minus t times this vector 3, 1. Now, when we have lambda is negative 5, we now have to solve A plus 5i, V equals 0. From before, we had negative 2 plus 5 is going to give us a 3, 3, 1, and negative 4 plus 5 is going to give us a 1. Just like before, if you're going to have non-trivial solutions, one of your rows needs to be a multiple of the other one. This is going to tell you that C1 is negative C2, C2 will be free, and you can then take your eigenvector here to be negative C2 and C2. You can write it like this. So this allows you to say, okay, this will be the second constant vector, and the second solution to my problem will be e to the minus 5t negative 1, 1. Now, if you want to check that this is a fundamental set, the Wronskian of these two is easily found. You're going to form a matrix. We're going to form what's called the fundamental matrix, where we simply take those two solutions, we plop them into a matrix. So we'll have 3 e to the negative t and 1 e to the negative t. Negative e to the negative 5t, e to the negative 5t. That's our matrix. Remember, we're taking those two solutions. The Wronskian will be the determinant of that matrix, and we'll get 3 e to the minus 6t, subtract another negative e to the 6t. That'll give us 4 e to the minus 6t, which is non-zero, and therefore this is, in fact, a fundamental set. The general solution is then just a linear combination of those two fundamental solution vectors. Now, if we want to write it a lot more explicitly, we would have e to the minus t into the vector 3, 1, c2, e to the minus 5t into the vector negative 1 and 1. Now remember, this means the first component is a function, the second component is a function. So if we wanted to explicitly write it out, we would have 3c1 e to the minus t minus c2 e to the minus 5t. x2 would be c1 e to the minus t plus c2 e to the minus 5t. Now, if we are given initial conditions, so as an example, let's say the initial condition here was given by 1, 2. We would apply it to this fundamental matrix. The solution that we were given, C1 x1 of t plus C2 x2 of t, we could write this as a matrix vector product, C1, C2, which means we could write this as the fundamental matrix times this vector of unknown coefficients, and that means little x of 0 should simply be the fundamental matrix at 0 times C, and this is what we want. So we will now have to solve this system where we have a matrix times C equals 1, 2, and the C is what we're looking for. So effectively, all we are doing when we go x of 0 is we are taking all of those exponential terms, putting them with a power of 0. What we'll get here is this system. Solve this system to find the result. You could use row reduction, or for this nice 2x2 case, you could say, look, these two vectors are always going to be coming from a fundamental set. That fundamental set is linearly independent. That means this matrix here should be invertible, and I'm simply going to apply the inverse to there. So this matrix inverse is going to be 1/4, 1, 1, -1, 3 into 1, 2. And this is going to end up giving you 1/4, 3, and 5. So C1 will be 3/4, C2 will be 5/4, and then your unique solution is going to be 3/4 e to the minus t into the vector 3, 1, 5/4 e to the minus 5t into the vector -1 and 1. Now note, when we solve our characteristic equation, if we have an n by n system, this will imply that we will get an nth degree equation for our eigenvalues. In the case that these lambdas are real and distinct, which was like the example we found, we have a theorem from linear algebra. So if a matrix A has distinct lambdas, lambda 1 all the way through to lambda r, then the corresponding eigenvectors are linearly independent. This is something you may or may not remember from your linear algebra course, but that immediately tells us another theorem. If this system x prime equals ax has real distinct eigenvalues lambda, let's say lambda I, then we have a fundamental set. And the fundamental set will always be given by e to the lambda 1 t times the first eigenvector, e to the lambda 2 t times that second eigenvector, all the way down to the last eigenvector. Now, the final thing to note here is that fundamental sets are not unique. In the same way that when you talk about R2, you've got the standard basis of I and j, you could have 2i and 2j as your basis, or infinitely many different bases. So if you have one fundamental set, you can put everything into this fundamental matrix X, and any other fundamental set will be related to it by the following. So if I have another fundamental set, let's say y of t, it will always end up being the original fundamental set times another matrix, and this is a constant matrix. If I have this fundamental set, let's say it's e to the t, e to the t, e to the minus t, and negative e to the minus t. So let's say that is my fundamental set. There's solution x1 and solution x2. Let's say I want to build two new solutions. Solution y1 is going to be two bunches of x1 minus an x2, and y2 will be one bunch of x1 plus three bunches of x2. Now, y1 is a linear combination of those basis solutions, so it will be a solution. y2 will also be a linear combination of those two, so it will be a solution. So there's still going to be a fundamental set. Note that you can kind of reverse engineer this, and you'll be able to find that this fundamental matrix Y, which is going to be y1 and y2 as the columns, you're going to be able to write this as x times the matrix 2, 1, -1, 3. By definition of matrix multiplication, this would simply be the matrix x2, -1. That would be the first column. The second column would just be x, 1, and 3. And that is, in fact, y1 and y2. What's important here is that the determinant of this matrix can't be 0. Because if it is, then you will no longer have a fundamental set. Because remember, the determinant of y has to be the determinant of this product, which is determinant of x times determinant of c. We know that this one isn't 0. And if this is going to be a fundamental set, that can't be 0. So this forces this determinant not to be 0.